Okay, so in the last example that we did, at the end of the last video, we sketched the graph of a function as well as a contour map for that function. This time we're doing this from a slightly different perspective. We're given some function f of x, y. We're not told what that function looks like as an algebraic expression, but we are given a contour map for it, and it says that we want to use this contour map to estimate f of negative 2, 6. So remember, these little red curves that you're seeing here, these are level curves for a function. So they correspond to the z value or the output of this function at whatever points in the xy plane they intersect. So, or they contain. Now notice here it says we want to use this to estimate f of negative 2, 6. So let's find the point negative 2, 6 on this contour map. Here's the origin. Negative 2 would be down here. 1, 2, 6. That's 1, 2, 3, 4, 5, 6. So right here, that's the point negative 2, 6. Okay? Now looking at our contour map, I can see that this point lies between these two contours, between 10 and 20. And it also looks like it's pretty evenly spaced between those two, pretty close to being in the middle. My best guess here is that this point, when plugged into our function, would give us something right around the middle of that interval from 10 to 20, say 15. So it looks like f of negative 2, 6 is approximately 15. Now I don't know how good that approximation is because, again, I don't know what's going on between these two level curves, between 10 and 20. It's unlikely that we're experiencing weird changes in elevation from 10 to 20. It seems like it would be a fairly steady uphill climb from here to here, but we don't know that for sure. So the best thing I could do is say that it's approximately 15. Okay. So we only have a little bit left to cover, but we want to change our focus a little bit to functions of 3 variables. Even though we can talk about functions of any number of variables. Think about that revenue function that I talked about in that set of examples at the very beginning of this section that had n variables in it. In this class, our primary focus is on functions of 2 and 3 variables. Because there's some specific things that you can do with those types of functions that you can't necessarily do in the more general case. So let's talk about functions of 3 variables. This one we want to find the domain of a function of the form f of x, y, z, given by this expression here, natural log of x plus y minus cosine of xy over z minus 2. And again, if I wanted to plug numbers into this, I'd be plugging an x and a y and a z into all of the corresponding variables here and producing that one output from that. But this is just asking for the domain. So for domain, finding the domain, we want to look for any restrictions that are implied by this thing. Starting with the natural log, I know that I can only take natural logs, or any log for that matter, of positive numbers. So that implies that x plus y here has to be greater than 0. Or equivalently, I can say that x has to be greater than negative y if I solve that for x. Okay, so that's a restriction that's necessary in our domain here. What else is a problem? Cosine of xy. Cosine has a domain of all real numbers, so it really doesn't matter what x and y are for this part of our function because you'll never have any issues with that. But we are dividing by something, z minus 2. That would imply that z minus 2 cannot equal 0, because then you'd be dividing by 0, or equivalently, z cannot equal 2. So how do we write this as a domain? Well, we're looking at the set of all x, y, z now. Remember, the domain in this case will consist of ordered triples, because that's what we're plugging into our function. The set of all x, y, z such that x is greater than negative y, and z is not equal to 2. Okay, just listing the conditions that we found here. All right, a little bit left to talk about. So when we talked about functions of 2 variables, we said that the graph of a function of 2 variables is actually a 3-dimensional it lives in 3 dimensions, I should say. Oftentimes they give us surfaces, like that hemisphere that we saw, or the plane that we graphed, or things like that. But then we showed, I can just go back here. We showed that even though that's typically how we graph functions of 2 variables, there is an alternative which requires 1 less dimension. We can graph functions of 2 variables in the plane by looking at level curves instead of the surface that we would get otherwise. We can do something similar with functions of 3 variables, and in fact we kind of have to if we're going to attempt a graph. Notice that here it says that if we have a function f of x, y, z and we want to graph that function, you actually need a 4th variable, because that 4th variable would represent the output of this function. Just like we set z equal to f of x, y, here I would set something like w equal to f of x, y, w, or sorry, f of x, y, z, and then find points of the form x, y, z, w, and try to plot those. The issue is that these points live in 4 space. They're 4-dimensional. You can't visualize 4-dimensional space, so we don't have a way of directly graphing these types of functions. We need some kind of clever workaround. And the workaround here is to generalize what we did with level curves, but this time calling them level surfaces. So the idea is that we, instead of trying to find all possible outputs w, we just pick a select few possibilities, set f of x, y, z equal to those. So again, I'm going to use k here like I did for level curves. K represents some constant. And then we take a look at the equations of this form, which would represent surfaces. So here's an example. Let's suppose we wanted to consider the function f of x, y, z equals x squared plus y squared plus z squared. I can't graph this thing directly because, again, we need a 4-dimensional graph, and I can't draw that. But if we set f of x, y, z equal to a couple of kind of convenient constants, and then just take a look at those surfaces, that might give us a sense of the graph of this function. So that's what's done here. If we set k equal to 1, for example, that's x squared plus y squared plus z squared equals 1. We recognize that as a sphere of radius 1 centered at the origin. If I set f of x, y, z equal to 4, then that would look like x squared plus y squared plus z squared equals 4. Sphere centered at the origin with a radius of 2. That's what you're seeing here. There's a 3rd level surface shown here. Z, we set this equal to 9, and that's another sphere centered at the origin, this time with a radius of 3. It's difficult to draw level surfaces just because it's already difficult to draw a surface anyways, if you're me and you're not artistically inclined. But on top of that, you're typically trying to draw several of those surfaces at once. So that's why you see the kind of holes cut out of these outer level surfaces, so you can kind of see into it and see what's happening in there. You're generally not going to be asked to graph level surfaces by hand. It's a pain most of the time, but knowing this concept is important for some things that we do later. One last thing before we wrap this up. Again, if we're talking about a function of several variables, say n variables, we think of the inputs for those functions as ordered n tuples. So again, right here from the very beginning, when we talk about functions of 2 variables, the inputs look like ordered pairs. Or functions of 3 variables like this one, the inputs look like ordered triples, something that carries all 3 variables. In the case of n variables, it's an ordered n tuple. That's what we call this. But it's usually, for notational convenience and some other reasons that we'll encounter later, it's usually pretty helpful to identify that ordered n tuple with a vector. So notice I'm calling this bold x the vector x1, x2, all the way through xn. You can think of that as the position vector for this point in n space. What I mean by notational convenience is that we can plug in this bolded x into our function f instead of plugging in the individual coordinates like this. Sorry, that's my son out there. So if I wanted to talk about a function of n variables, but I've identified these ordered n tuples with a vector, this is just shorter to write than this is. So again, it's a kind of about notational convenience, and there's some other benefits to this that we'll see later on. No examples that I want to do with this, just want to introduce the notation to you. Okay, that's it for 14.1.